So with that out of the way, my name is Andrei. I've already presented hardware in the morning. To recap, I work on sensor simulation as well as some state estimation at Waabi. And in this session, we're going to be talking a bit about how we gather data, what the techniques are for curating interesting and useful data sets, and how to actually label them into useful artifacts that you can then use for supervised learning. So let's get started. So as you all probably know, datasets have been a crucial part of the recent advances in all tasks of machine learning. And this ranges from things like low-level vision for things like stereo estimation and optical flow, all the way to more advanced tasks like object detection and motion forecasting. And it's worth pointing out that when I talk about datasets, this means both labeled as well as unlabeled datasets. And of course, since there's been growing interest in autonomous driving, so too has there been a significant increase in autonomous driving related data sets. And starting with one of the very first ones, definitely the most popular data set, Kitty, in 2012, we have seen data sets for tasks like perception, motion forecasting, actor behavior, and motion planning constantly being released ever since over the last decade, constantly improving in terms of their scale and diversity. Okay, so before we get started into how we actually curate and label datasets, it's important to kind of think about the datasets that we plan to use and the kinds of features that we would like them to have. Like, what do we actually want from a dataset? There's no one-size-fits-all solution. So depending on the tasks you're trying to solve in robotics, the dataset choice might be different. So there's a few properties that we can consider when looking at different data sets. So first, there's the sensors that we use to collect the data set, which can vary significantly, and they have a large impact on the kinds of models you might want to use and the difficulty of the task. So for example, in autonomous driving, there might be data sets that emphasize radar perception more. There might be data sets that focus on motion forecasting or long-range perception and so on. Second, the presence or absence of high-definition maps is another factor. Maps can potentially provide useful supervision or priors for many tasks. And some datasets contain no maps, while other datasets might contain very detailed high-definition maps with a lot of annotations for crosswalks, lanes, as well as more abstract information like, I don't know, traffic light information and construction elements and so on. And third, of course, supervised machine learning models are as good as the labels that they are fed. So the type of annotations, their quality, their quantity, their granularity is the final factor that you need to consider when deciding on what data set to explore for a specific task. And finally, as we will discuss later, dataset curation techniques can be applied to one or more datasets in order to ensure that the examples in this dataset are more interesting and more representative for your task at hand, while also covering kind of real world scenarios. And the coverage is crucial because you want your dataset to cover the distribution of real world data correctly in order to generalize to the real world. Okay, so we've already talked a little bit about sensors in the hardware section, and then later on we'll talk about more details of mapping. And for now, we will focus more on the curation and the labeling slides. Okay, so what are the actual stages that encompass this sort of a traditional dataset building process? Well, you have to begin by collecting some sort of raw data. Then you curate it in order to extract interesting parts of this dataset. And then you typically feed this data to some sort of labeling system, traditionally relying on human annotators. And then the resulting dataset is finalized, and we more or less keep it fixed for a time for comparison purposes. We use it to train models, and then we use held out labeled data to evaluate. However, there are some remaining challenges with this kind of framework. Namely, even a handful of autonomous vehicles can collect thousands of hours of data over a relatively short time span. And you need to select the best data to train on and to potentially label. And this is not an easy task because it involves balancing basically many metrics. And of course, while effective, human labeling is pretty expensive, which means that it is very difficult and expensive to scale to very large data sets. So we need to come up with ways which can leverage human annotations only when truly needed. So the focus of this talk is on these two stages, namely data curation and labeling. And we will begin first with curation, namely answering the question, okay, given a huge pool of raw data, how do we actually curate an interesting, useful, and representative data set? Before diving into specific curation techniques, as before, we need to start with the desired properties that we might want to optimize as part of our curation process. First, we would like a data set to be interesting and to contain challenging scenarios that are useful for training our models. Of course, this definition of what is interesting can depend a lot on the task, and we will see some specific examples in a bit. Optimizing for coverage, on the other hand, ensures that the selected data set that we picked is representative of the real world, such that we can generalize to real world scenarios. And last but not least, given a particular model that we're interested in, we can also consider optimizing the data set itself in order to further improve this model's specific performance on the task. So let's now start first with approaches which seek to curate an interesting data set. Rules-based tagging lets programmers write custom tagging logic, which decides kind of algorithmically what is interesting. So typical inputs to this rules system can be things like perception outputs, the pose of the ego vehicle, and maybe even an HD map. Now, the perception outputs could be the ones that you already recorded while you were recording this data and your autonomy system was running, or you can compute it after the fact. It doesn't really matter. And the idea being that you have this set of data, you process it and run these kinds of custom scripts, and whenever one of these scripts finds a match, you flag this with a particular tag, and then you can query for tags when you're building the data set. And of course, there's a long list of attributes that you might want to consider when you're building these kinds of taggers, and which could be used to define the interestingness of a scene. So you can have tags that are related to a map, to the actors within the map, or to your own behavior. So things like, for example, the map complexity, specific kinds of interesting intersections. Actor complexity might be the number of actors and their overall aggregate behavior. And then ego complexity, you can look for things like harsh braking, excessive speed, or any other interesting, unusual occurrences. Now, this rules-based system can be very powerful, but it does require significant engineering to actually write this kind of tagging logic. And the tagging logic itself, at the end of the day, is kind of handcrafted. So in many cases, it could be brittle to things like noisy perception outputs or some changes in your models. So one other approach is instead to directly learn to tag by essentially training a network which, given some sort of raw data, maybe even the raw sensor data, it directly outputs tags of interest in a scene. For example, is there heavy traffic here? Has a cut-in occurred through this sequence, etc.? And this approach can be more flexible and robust than the previous one. But of course, the disadvantage is that if you cast this, for example, as a supervised learning task, then you will need a training set for each of, you will need the supervision labels for any possible tag you're interested in, which is also not the most scalable thing. One other thing to highlight is that the approaches that we're talking so far kind of have been making this assumption of a fixed set of tags for any self-driving scene. Like, is there a cut-in or not? Is the vehicle braking, etc.? Is there heavy traffic? But in the real world, there's also an extremely long tail of scenarios that we might be interested in that would fail to be captured by this kind of fixed set of tags. And basically, this motivates the use of an open set tagging system. And fortunately for us, recent advances in vision language models are a very promising direction for helping us capture this long tail. The idea being that you can then learn to leverage shared embedding space for your sensor observations and some sort of text, something you can think of as a clip-like application, and then leverage this for zero-shot classification of novel occurrences. Now, later works have extended these kinds of basic ideas to more elaborate use cases. For example, doing things like open set object detection and open set segmentation. So, instead of segmenting all the cats in an image, you might have a prompt that says, I don't know, like segment only dogs that are riding a skateboard or something. And then this would try to kind of figure this out, but produce actual structured outputs. The idea behind these methods is essentially that you use some sort of pre-trained clip-like embeddings, and then you fine-tune additional heads for perception and segmentation and so on. And then you have, of course, interactive question answering, which basically takes this one step further, and it allows for more complex text prompts beyond, perception labels, and lets you do more complex reasoning. And recent works do this by, for example, leveraging recent advances in vision language models, like, for example, GPT-4, and then they potentially even collect additional data sets for fine-tuning these models for self-driving applications. And in many cases, it's been shown that these models are actually powerful enough to aid with the driving task itself, so to be used for autonomy, like natural language kind of guidance for both interpretability as well as autonomy, which highlights that these systems are powerful enough for a wide range of tasks, including things like data curation. Okay, so we've seen that the idea of optimizing for interestingness can lead to significant improvements over a bunch of different models as well as tasks. But given a particular model in which we're interested, it's now also natural to ask whether we can specifically select examples to label for this model such that we optimize the performance of this model. This can speed up training, and it can also ensure that you're using your labeling budget very, very intelligently. Of course, what I just described is a well-known machine learning problem called active learning. And the idea behind active learning is that you iteratively leverage the current trade model to decide which examples to label next based on those believed basically most likely to improve the model performance. Now, directly optimizing the expected improvement of a model in the real world is, of course, a very challenging task. So in practice, this is often approximated with a related objective. Like, for example, you might select samples which have high model uncertainty, or they might induce a high information gain. You can use output entropy as well as the notion of a margin for classification in order to select what to label next. And this can basically do quite well in practice, but you're still limited by the fact that these kinds of approaches struggle when something is completely off distribution, because in general, it's challenging for a model to learn well-calibrated confidences on unlabeled examples. And within the self-driving industry, multiple companies have mentioned the use of some version of active learning as a core component of their development approach. And these approaches are basically more engineered, productionized versions of the uncertainty or entropy-based criteria that we saw previously. So one example is for Tesla's Autonomy Day, they spoke about automatic triggers, which can identify examples to be sent to labeling automatically in order to improve the system. And another example is some blog posts from Cruise that also talk about how they leverage the consistency of trajectory projections over time in order to mine for hard examples. The idea being that, if you're doing your motion forecast for some particular object at time t, you have your data already recorded, so you can look at where that object actually is in the future. And if the object ends up at a completely different location than when you predicted it, you can flag this snippet for labeling and then add it to your data set as a challenging example. Now, a lot of these systems do require a fair bit of human in the loop. And recent work has actually studied ways of bypassing this altogether. So a CVPR 2024 paper called AID actually builds on this idea, and they propose building a framework for automating this kind of data engine that you see in the industry using large language vision models. The idea being that this paper leverages an image captioning model to find issues with the detection model. And it automatically queries for additional examples of this kind of issue from a large database of raw data using another VLM. And then it uses a zero-shot detector to generate 3D labels to continually train the model. And then there's also this verification module that lets you kind of have a measure of confidence such that you don't ask for human corrections for every single correction of these, which means that you are actually maximizing the efficiency of your training and having the model kind of improve itself over time. So let's now turn to the final curation objective, which is diversity and coverage for the data. Now, selecting only interesting or uncertain examples is very good in theory, but it can also lead to a biased data set, which actually ignores common, less interesting scenarios. For example, as highlighted in this picture, you might miss the area on the bottom left completely. And for machine learning systems to generalize, it is also critical that the curated dataset is representative of everything in the real world, right? Not just the challenging cases. So selecting a representative subset of the total samples, which covers the true distribution, can be formulated as a set selection problem. So you can specifically formulate this as a core set selection task. And here the goal of core set selection is essentially to find a subset of samples such that when you train a model on this subset, its performance is still very good on the remaining samples that we did not select. And in general, finding the solution to this kind of problem, the case center problem, is NP hard. But in practice, greedy algorithms have been shown to be very promising. So specifically, you can do some sort of iterative selection where at every time step, you just select a point that has the greatest distance to any of the previously selected points, or you could just pick something that has the greatest median distance to the selected points, and you do this iteratively, and you keep selecting interesting samples such that you have good coverage, but you only need to label a fraction of your raw data. Now, a question arises because we're now talking about a lot of distances and median distances and maximum distances. So the question now is, what space should we do this selection in for coverage or diversity-based sampling? One common approach in active learning is to actually use a learned space. So for example, the second last layer of some neural network you're training, or you can use a completely separate model that is pre-trained in a completely unsupervised way. And you use that as a feature learner, and then you use these learned features to embed examples into a feature space. And then in autonomous driving, what you can actually do is you can leverage a more handcrafted approach for these selection processes, where you might include attributes that you'd like to capture regardless of everything else, like even coverage of the geolocation or even coverage of lighting conditions or whatever, potentially in addition to whatever features another model is learning. So to summarize, we've reviewed essentially these three categories to curate self-driving datasets. And of course, there's no one-size-fits-all approach. And typically, you might want to do a combination of these approaches to ensure that the dataset covers the long tail of examples well, while also having even coverage for any potential real-world example in order to train robust machine learning models. Okay, so now that we wrapped up curation, let's look at ways for scaling up labeling. Now, the most common way to do any sort of labeling is to employ humans. And this can usually do really, really well and produce the highest quality annotations possible, but it also requires manual effort, so it's therefore pretty expensive. Now, for tasks like motion forecasting, as we hinted at in that example from Cruise, you can actually use the output of an onboard perception system itself for the annotations, because you no longer are restricted to a limited view of the time dimension, so you can compute very, very accurate trajectories offline and use these to supervise prediction. Now, these results are still kind of noisy, so while they can be useful for training motion forecasting, you cannot directly use them to improve the detector itself. So this motivates the growing interest in automatic labeling or offline labeling models, which can leverage future information as well as more computational resources in order to obtain high quality data labels, while also being able to run at really large scales on compute clusters without the need for human intervention. So here we'll provide a quick overview of the most common sort of paradigm for this kind of automatic labeling pipelines. And in this case, we will be focusing on a LiDAR-based approach, but a lot of these concepts also apply if you're only dealing with camera data, for example, or radar. And there's a lot of methods that have appeared in the last few years in this area, but a lot of them follow a similar framework, even though they differ in more subtle ways. So in the first stage, you begin by running a traditional object detector on your raw data, and that will give you some initial detections that you can then process with an offline tracker to obtain tracks over time. And then you can use this as a coarse initialization to a second stage refinement model, which is trained to refine each of these trajectories independently. And then once you have these refined trajectories, you can then leverage them as labels to train your regular old perception model. Now, one limitation of this approach is that, well, you still need human labels to supervise the automatic labeling system itself, particularly the refinement engine. And then A separate line of work seeks to bootstrap perception systems without relying on any labels at all. So these approaches often leverage the fact that self-driving vehicles might be visiting a specific area of the world multiple times, and use the fact that this will give you a sense of what parts of the environment are static versus dynamic. So what this can do is that it can help us essentially bootstrap a perception model from heuristic labels that we figure out based on this kind of differences over time, and then use those labels, those very, very coarse labels, to train a model, and then use this model to relabel our data, then prune the outputs with some sort of heuristics, and then continue this loop of self-training, which, as it turns out, doesn't plateau as early as you might think, and can actually lead to pretty decent results. Recent papers have even started using applications of RLHF, reinforcement learning from human feedback, a very powerful technique that has seen has shown a lot of benefits for training large language models, and they've been using this to improve the process for the self-training instead. But here, of course, they would be potentially replacing the human feedback with, for example, human handcrafted heuristics instead, like some sort of shape or alignment priors on the kind of labels you're expected to see. So the nice thing here is that you can kind of have a human engineer a few of these heuristics, and then they kind of get reused over and over by the model during this self-training loop. And then you end up with a pretty good detector, even though you didn't have any human labels to begin with. So to recap, in this talk, we focused on intelligent data mining for building self-driving datasets. Namely, we began by talking about data curation strategies, for example, using handcrafted rules to tag interesting parts of the data versus vision language models to do the same thing. Then we talked a little bit about how to ensure nice coverage of the data to make sure we're not too biased over safety critical scenarios and forget about the boring ones. And then finally, we talked about how to actually label the data set that we've now curated and how we can actually improve the label efficiency by using offline perception methods or even some sort of bootstrapping process that requires no human labels to begin with. So with that, we've reached the end of the intelligent data mining session. We'll have time for a couple of questions, and then Siva will talk about extending perception to multiple vehicle settings, and then we have the simulation settings, the simulation sessions. Thank you very much. Awesome. This question?
So, that, so how do you tackle the increasing amount of data throughput? So basically, if you want to scale up your systems, you probably the increase amount of flux, and the through time the bit amount will also increase. So probably like it's not economic to train your model every time you collect new data, especially in a paradigm of pre-training and fine-tuning. Probably for fine-tuning, you can like train your model each time you collect new data, but for pre-training, it's extremely expensive. So how do you tackle this kind of increasing amount of data issues? Do you apply some kind of continual learning algorithms in your system?
Yeah. So the question was, given that it's not the easiest thing to keep retraining a model over and over, how do you deal in practice with the fact that you constantly have new data arriving that it is getting added to your data set? So I think, so I haven't worked directly on this kind of stuff like continual learning, but I would imagine that it is possible to keep fine-tuning a model without retraining it from scratch every time as new data arrives. I'm not saying, I don't think it makes sense to retrain it every day or anything like this, but I think it's worth experimenting to pick a good trade-off between not having gaps that are too long between model retrains, but also not spending too much money, and then having the model kind of automatically get trained for like maybe an epoch on the latest, greatest data, while also making sure to have a very robust and well-designed validation set for all of this.
Waabi, like, are you like training your model from scratch? Training your model from scratch every time you iterate, or you kind of still utilizing some previous
I can't give any like super specific details about the perception setup, but in general, yeah, like I mentioned, it's not really economically feasible to retrain too often, especially if your model is very large. So that's why it's typically you have some sort of cadence that you need to decide on by experimenting in your particular use case, and then using this to decide, okay, I'm gonna do incremental retraining every, I don't know. Again, these are just examples. I actually don't know. Like you can have like an incremental retraining like every week, and then I don't know, every month you do like a from scratch run or something like that. And of course, using a lot of validation data for this. Yeah. Yes, question.
All the retraining, talk about millions of data getting to the system. So how you select of the data into the labeling equipment? You might have to ingest everything. So thinking about gigabyte of data that you want.
So is the question specific to curation, or is the question specific to how do we actually go even before curation? How do we actually ingest?
You have to ingest everything, so like the label curation process and how you.
Yeah, I can answer that. Yeah, so the question was, okay, how do you actually deal when you have to ingest like petabytes and petabytes of data? So yeah, I can of course, as before, I'm gonna answer this academically. I can't give like specifics, but generally speaking, in my experience, it is important to have an efficient system for ingesting data, even if there's like a lot of data coming in. Now, about storing data long term, you can leverage some coarse tagging to, for example, decide what is definitely not interesting and what you can get rid of versus stuff that might require further inspection. And you can combine that, for example, with things like lossy compression to improve efficiency and keep your cloud costs down, even when you have a really large number of data streams coming in. Sorry, yeah, it's the one in the back, and then you, yes, and then we can move on to the next session.
How to accommodate synthetic data into real data in your pipeline? You haven't talked about synthetic data, so it's all about real data. But we know that there are conditions that we need synthetic data for performance. How you mix it with real data in your pipeline?
Yes, that's a good question. So we will see more details in the coming sessions. The session, not this one, but the one after, will talk extensively about simulation, and it will also include how to use simulated data to improve perception systems. But yeah, I agree. Generally speaking, you have similar issues with simulation when it comes to, you still have to store the simulated data and tag it and so on, but you can reuse some of the tagging ideas to find interesting things that happen in simulation when you're running simulation at scale. And then in terms of actually mixing the data when you're training a model on both simulated and real data, there's like a lot of literature on domain adaptation and multi-domain training that can be applied to make sure that the model doesn't cheat too much when it comes to mixing the two domains, and that the gains you get from adding simulated data actually materialize in real data. Okay, one more question.
I have a question regarding the data curation. If my understanding right, you mentioned the data curation is one of the ways to selecting this data itself. You use the very last, the second layer of the model, which really is to identify the distribution of the labels. Can you elaborate more?
Yeah. So this was, for example, you can consider things like a perception model that is pre-trained, and then you might run the perception model on these data samples, and then the final activation feature map, maybe before your detection decoder or something like this can be turned, maybe using PCA to reduce the dimensionality, into a feature vector that you then use for various distance calculations and diversity metrics. And if you don't have this model to begin with, you can also use some sort of pre-trained self-supervised model that is trained using some sort of, I don't know, like masked autoencoder or some unsupervised learning technique like that.
Well, that selection logic itself applies to the model we choose.
Yes, so that's a good question. So when you go to that point, you will have some sort of bias towards the specific model or maybe even the architecture you're doing. So that's why these hybrid approaches are useful, where you're kind of using some models features in conjunction with some other rules, like for example, geographic coverage or something like that. So usually having a hybrid approach can help mitigate some of the model specific bias. Yeah, you're welcome. Should we get started with the next session? Okay.